This is Dr. Nerz. Unfortunately, this morning when I gave my lab lecture, the Tegrity did not work, okay? And I'm really sorry about that. That was supposed to be your lecture. Because I'm having a medical procedure tomorrow, Tuesday, February, whatever it is, 19th, 18th?
18th.
I will not be in giving lecture, okay? However, someone is taking my place for lab, Dr. Perello, and she'll be running the lab. This little video is in lieu of the Tegrity video, which I wish got recorded. So please watch this, okay, and realize it's going to be very, very, very similar to what I did this morning. Maybe in some ways it's better because in the lecture hall, it's actually really hard to read the board, as you know. So I hope you can see this. All right, so what are my goals in this little lecture? My first goal is to talk to you in general about the project and the kinds of things you have to do to keep the project rolling, okay? The second thing I'm going to do is I'm going to give you a general overview of the project. I'm going to tell you what we're doing, why we're doing it, and what we're doing chemically. And then the third thing I want to do today is go over the aldol reaction, which is the first reaction most of the students, or I should say all of the groups, will be doing this week, okay? So first of all, what is really important? You're not going to have a lot of assignments during this time period, okay? But what is expected is that you're going to keep a really good notebook. You should be writing everything down, every procedure. If you scale the procedure, write it at the scale that you did it at. If you make any particular observations, if you have any apparatus that you've never used before. For example, next week you're going to be learning about column chromatography. You should diagram that out in your notebook so you know what you're doing. If you do TLC plates, you should draw diagrams of your TLC plates. Okay? If you do spectra, put the spectra into your notebook so that you have them. I would also say that as you go along, interpret things, okay? You should be interpreting your spectra as you go along. In about 2 weeks after I get through the theory behind this project, I will be going systematically over how to write a research paper. Each group is going to be responsible for writing a journal-style paper. We're going to pick a journal. We're going to follow the format of that journal. As I often say, writing a journal-style paper is not immensely creative. In fact, there are, templates out there you can use to write papers. Okay, it's not that creative. It's more that you just have to follow format. The creative part is in designing the experiments and in interpreting the experiments. So your interpretation might be rather creative, but the actual writing of the paper is kind of a systematic thing. I'm going to go through and talk about how you write an experimental section, how you write the introduction, how you write the discussion, and we're going to work on that over a series of weeks. What I would recommend is rather than waiting till the last minute to write the paper, which will probably only be 5 or 6 pages long, you should be writing as you go along. So for example, I'll probably do experimental sections first. If you have finished a procedure and you have all your data and you've been interpreting it as you go along, you should write those up as you go, okay? And you can do it all on Google Doc together as a group, all right? So, kind of plan on that because we don't have a lot of written assignments. One thing I want to add, and I will tell the whole classes too by email, you do have a quiz next week, okay? That's probably the only written assignment over the next few weeks. That quiz, okay, is going to be on complex splitting, especially as it applies to ethyl acetoacetate, the reduction of ethyl acetoacetate, okay? So quizzes, as usual, are going to be kind of spectroscopically oriented, all right? Possibly something on flutamide too, the spectrum. Okay, keep that in mind. Don't forget that. Okay, so goal number 2. I want to tell you a little bit about what we're doing, all right? This lab centers around warfarin and warfarin analogs. Okay? All right, warfarin is or at least was, one of the most commonly used anticoagulants in medicine, and people still use warfarin. What is it used for? It's used for people who get blood clots or to prevent blood clots, okay? Basically, what warfarin is warfarin is an inhibitor of an enzyme called vitamin K reductase. Vitamin K reductase, as the name implies, is involved in a redox process, okay? Ultimately, this process results in the carboxylation, in other words, the addition of carboxylic groups to certain amino acids that are on platelets. And when these groups are carboxylated sufficiently, this is part of the initiation of the coagulation process of platelets, which can result in the formation of blood clots. This drug is immensely, so again, the idea is warfarin takes the place of a molecule that would usually initiate the process, but instead inhibits the enzyme. In other words, it binds the binding site, shuts the process down, and stops coagulation, stops a redox process that occurs. Okay, and we're going to go into that in more detail as the weeks go by. We have lots of stuff to learn. I want you to start reading about it, okay? And a good place to start reading, of course, I hate to say this, is Wikipedia. Not a terrible place to start with this, okay? Now, you might wonder, why would it be of some interest to make warfarin analogs? A warfarin analog would just be a compound that's like warfarin, okay, but is somehow structurally altered. Now, we could do this in a much more design-oriented way, which we are not doing. We are doing it in a more random way. But the idea here is we are going to create, using a very successful reaction, a library of compounds that vary slightly or significantly from the structure of warfarin, but still have the same basic structure of warfarin. And what we're hoping is perhaps we could create molecules that have greater efficacy and have lower toxicity. And by the way, warfarin is one of the most difficult drugs to dose in medicine because it is not metabolized the same by everybody. So the problem is when people get the same, like two people that have the same weight, say, are given warfarin, one person might metabolize that differently than the other person, and one person might have a much higher concentration of warfarin or a longer lifetime of warfarin in their system than another person. So the problem is, you know, for one person, the same dose could cause like intense bleeding, or the other person, it's the correct dosage for clotting. So you actually have to do tests on people constantly when they're on warfarin. So it's a very successful drug in some ways, but also a very hard drug to use. So it'd be of some interest to get a drug that, say, was of greater efficacy, lower toxicity, or perhaps metabolized more uniformly. That would be of some interest. Realize warfarin and their analogs have all kinds of biological activities. As I told my class this morning, I got a little carried away, but I was talking about 4-hydroxycoumarin. Compounds like this have tremendous biological activity, and you'll find compounds like this in, say, green tea. I was ranting on and on this morning about how it's found in papaya leaf extract. Not 4-hydroxycoumarin, but compounds that are like 4-hydroxycoumarin. And believe it or not, you know, I've told this story many times, but a couple of years ago, I was having trouble with my platelets, and one of my students told me that in Bangladesh and in the, you know, in the Southeast Asia, and in countries where they have dengue fever, people frequently take papaya leaf extract, which has a lot of these hydroxy aromatic type compounds in them. They take it to raise their platelets. And in the literature, it said, I looked this up, and so the student said to me, "You have low platelets, Dr. Nerz, you should take papaya leaf extract. If you take, it works on dengue fever. In dengue fever, your platelets go down, and when people take this drug, it raises their platelets." So I looked it up in the literature, and I'm not one to take botanicals in general. I'm very scientifically oriented, and I'm a little leery of stuff like that. And it said that, hey, you know, dengue fever is an infection. What's happening to these people is they go into the hospital, they start taking the papaya leaf extract a few days later, and they're already recovering from the fever. So it has nothing to do with the platelet extract, right? So I was having this problem. I really had tremendously low platelets, and I decided to try it. So from Amazon.com, I ordered this bottle of papaya leaf extract that cost about 30 bucks, and I'm like taking a swig of it every morning before I go to work. And lo and behold, my platelets go way up. I tell my doctor about this, who's an oncologist. He starts using it on all these different patients, and I believe it's now 6 patients now, 100% result. So you say, oh, why don't doctors use this, right? Why don't doctors use this? So we really got into this and really started studying it, and we discovered that, you know, papaya leaf extract has many, 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 many compounds in it. Now, the pharmaceutical industry has come up with a drug to raise platelets. It's the only drug, successful drug. It's called Promacta. And I studied Promacta, and I tried to figure out if it had any relationship with the compounds that I know already exist in papaya leaf extract. And we were hoping to try to figure out what the active ingredient is. But the reason doctors are not interested in the papaya leaf extract, my doctor is, but most aren't, is because it has so many compounds in it. Okay, it has so many compounds in it. And it could be some combination of the compounds that result in the biological activity. So again, why do I bring this up? Because of the complexity of biological activity, the structural relationship to biological activity, right? And the idea that perhaps taking this basic framework that has such biological activity, this itself, I believe, has anticoagulant activity. A lot of these compounds have antifungal activity. A lot of these warfarins do. Antifungal activity, antibacterial activity, anti-cancer activity. There's all across the board. So we're going to create this library of compounds that have potential but biological activity. Maybe some compounds will even raise platelets. I don't know. Okay? From the basic warfarin framework. Okay? So how do you make warfarin? All right, so this is kind of the rest of my introduction. Warfarin itself is made by taking 4-hydroxycoumarin. There's a lot of ways to make it, but this is one way to make it. 4-hydroxycoumarin, and this compound right here, and I'm sorry about my shadow, is called 4-phenyl butene, for my folks that are doing nomenclature right now, or did nomenclature recently, butene 2-one. Okay, 3-butene 2-one. So it's 4-phenyl, 3-butene 2-one. Okay, is this compound up here. You take this with this in the presence of acetic acid, THF, and a catalyst that's called depent. Okay, and we're going to talk more about this. There's a lot of chemistry here, and you're going to see the chemistry is all carbonyl chemistry. So you're going to see, oh yeah, I learned that in class, or I'm learning about that in class right now. So my class right now, we're spending like a month on carbonyl chemistry. You're going to see all these reactions coming up in class if they haven't already. Okay? So the basic idea is that this carbon here, which I'll focus on, links into that carbon there through a conjugate addition. Okay, to make warfarin. All right. So if I were going to draw the structure of warfarin, so this is my reaction, and what you're going to do is we're going to alter this. We're going to use different variations on this, and we're going to use different variations on this to make a family of compounds. Every student is not going to be responsible for the whole family, but as a class, we're going to make a family of compounds, and we plan to make some new compounds, which is kind of exciting. Okay. Now, how would this look? How does warfarin look? To make life simple, I'm going to use the structure I already have up here. And the weird thing about this, I felt like last year, through most of the semester, I guess I failed as a teacher, I don't know. But through most of the semester, I just felt like people didn't understand what we were doing. They kept saying, what are we doing? What are we doing? And I kept saying, we're making analogs of warfarin. All right, so this is the structure of warfarin. Okay, again, it's obtained through a conjugate addition into that alpha-beta unsaturated ketone. It has one asymmetric carbon, which is right there, and it's actually more active in one form than the other, and you can read about it. And depending on the catalyst I use, that depend catalyst, I can make the R or the S compound. Okay, we can control that, or we can make the racemate if we want. Okay, so that's warfarin. So what are you going to do? Well, you're going to make variations on this structure, and you're going to make variations on this structure, and then you're all going to use the same coupling reaction or alpha-beta unsaturation attack to combine it. Then we're going to make different compounds which would presumably have different biological activities because their structures are different, right? You change the structure, it may not bind the enzyme anymore, or it may bind the enzyme more tightly. You know, that's the kind of thing we're interested in. Maybe it'll have antibacterial activity. Okay, so these are the two pieces you have to work on. We're starting with this piece, and I really apologize for my shadow. All right, we're going to start by making variations on this, on the alpha-beta unsaturated compound, and I'm focusing on that today. Okay, that's what I'm focusing on today, mechanistically. Okay, what are you going to do? Are you just going to make that? No, that's boring. Okay, that, you could make it. You have the ability to make this. However, this is uninteresting. It's super cheap. We could just buy it. We're not making that. What are we going to do? We're going to do variations in this position and possibly in this position. Okay, so we're going to stick other groups on there. Or you're going to build molecules that have other groups on there, and then you're going to incorporate that into your warfarin synthesis so that you make a molecule that's warfarin-like, but is not warfarin, okay? And it maybe has different properties. Now, a synthetic chemist looking at this is screaming aldol reaction, okay? Why is it screaming aldol reaction? Because this is what you call an alpha-beta unsaturated ketone. Okay, so to a synthetic chemist, they're like aldol. Why? Aldol reactions make alpha-beta unsaturated ketones. Now, for those of you who are not, oops, my alpha and beta are in the wrong position. For those of you who are not into this terminology yet, and that's possible, you're used to the term beta being used for elimination reactions, okay? In carbonyl chemistry, the carbon next to a carbonyl is called the alpha carbon, and then the next one down the line is beta. So using the terminology alpha-beta carbons, unsaturated, double bond. You might already be thinking about that and saying, why would a molecule like that form, right? You're going to see in this reaction that this is the thermodynamic sinkhole. In other words, molecules are just going to be driven to form this molecule. Why? And you should say conjugation. There's a lot of conjugation in that molecule. All right, synthetically, alpha-beta unsaturated ketones, or aldehydes, are close relatives of, how am I doing time-wise?
18 minutes.
Okay, good. That's not too bad. They're close relatives of beta hydroxy. This is called a beta hydroxy ketone. This is looking at it synthetically. So these are retrosynthetic arrows. So if I'm an organic chemist, I'm looking at this. I go, you know, that's an alpha-beta unsaturated ketone. Then I would say to myself, what do I make alpha-beta unsaturated ketones from? I make alpha-beta unsaturated ketones from beta-hydroxy ketones. Okay, and by the way, when we did our reduction of ethyl acetoacetate with yeast, we actually made a beta-hydroxy carbonyl compound. So we made a kind of an analog of this, which is sort of interesting. An organic chemist looking at this goes, I can make that with an aldol reaction. And although it is true that 2 or 3 years ago, the chemists of the world were surveyed, and I told you that the Diels-Alder reaction was the 3rd favorite reaction of all organic chemists, I can tell you that the aldol reaction is my personal favorite reaction. I won't tell you why, but it is my favorite reaction. So, and you might say, well, what's so great about the aldol? See, here I go, I'm going to say why it's my favorite, but what's so great about an aldol reaction? Aldol reactions are pretty cool because they occur in nature, okay? This structural motif, where you have a carbonyl with a beta-hydroxy or an alpha-beta unsaturated, particularly this motif, is very common in nature, and it's very common in antibiotics and in biologically active molecules. And the other thing that's cool about it is chemists have really rendered this reaction very controllable. So, in other words, I can tell you we can do aldols in such a way that we can make a single enantiomer just the way nature does. So this is a reaction that we have really mastered, okay, like nature. So we can almost compete with nature on this. And again, this structure does show up in a lot of biologically active molecules, so you have to know how to build it. So we do our own aldols. So this is an aldol type product, okay? And again, thinking backwards, like a synthetic chemist, okay? I would look at this and as a synthetic chemist, I would say I can make that from this. And again, you guys are going to work with analogs, so you're not going to do the exact reaction necessarily that's in your procedure. That's just sort of like guidelines for you guys. So what would this come from? This would come from this. Plain old acetone and some sort of a benzaldehyde. And again, hopefully a substitute of benzaldehyde. So just for example, out in the lab we have aldehydes that have chlorines, we have aldehydes that have oxygens, we have aldehydes that have nitro groups. We have all different groups that you can put there, and we could have more, all right? We're trying to give you things that work reasonably well. So if I take this, I can get this carbon to attack this carbon, reduce it, and I'll have that alcohol. Okay? Now, let's look at the chemistry a little bit. All right? Now, when I do these, I do them the way you do Diels-Alders. In Diels-Alder reactions, the numbers are of paramount importance, and they're extremely helpful in putting the structure together. And in aldols are no exception, okay? So in general, I'm going to show you how we use numbers. In fact, in my lecture, I think I used A, B, and C instead, and I may switch to this methodology. But in general, an aldol, and this will be sort of the end of my lecture, an aldol, what you do is you have an aldehyde or a ketone. I'm going to call this R1. I'm going to call this R2, aldehyde or ketone. Then you have another, I'll call this R3. I'm going to call this R4, and I'm going to call this R5. This is a little bit ridiculous, but you'll get the idea. So in an aldol, what I must have, and they can be very complicated, I must have what is called an alpha hydrogen. Okay? I always call this carbon here, I'm going to call this A, this B, and this C. I always call this carbon the attacker. This is not official terminology, this is my terminology. And then I call this carbon here, C, the attack E. Okay? Attacker, attack E. All right? In the reaction, what you do is you add base. I'm going to do the actual mechanism of your reaction, usually done in something like ethanol. This is not the most sophisticated aldol, okay? And in the reaction, what happens is this proton comes off, this B attacks the C, this opens up and it picks up a proton. So you always end up in an aldol with this basic structural motif. And I'm writing it backwards. This is A. A is sort of like a facilitator. B is the one that attacked. C got attacked, and when it got attacked, it got reduced down to an alcohol. And we're going to do the mechanism in a second. That's the frame of any aldol. All aldols give that ABC structure. All you have to do is, just like a Diels-Alder, what's carried along for the ride. So you go back to A, and you say, oh, what was hanging off of A? And you say, oh, R3 is hanging off of A, right? What is hanging off of B? you know, because I was being sort of liberal, I put two groups here, R4 and R5. I'm not saying those can't be hydrogens. They could be hydrogens. Okay? And then I'm saying on C, I would have R1 and R2. Now, the reason I did it that way is some aldols, it's kind of hard to tell what the product looks like. And if you do it like a Diels-Alder, where you say, I always get the same frame, just what's coming along for the right, I'll fill it in. Okay? So let's look at our actual aldol, and then we'll be done. Okay? So, and like I said, what we're going to do, I'm going to keep reviewing each week what we're doing, kind of keep you on track. You know, if you don't get what's going on or why we're doing it, please come and talk to me. And I told the class this morning, I said, you know, I had one of those moments. I said all semester I kept saying, everybody kept telling me we don't know what we're doing, we don't know what we're doing, we don't know why we're doing it, we're just coming into lab. I want you to really be thinking, keep the big picture in mind, and then every week kind of chip away. And I'll just tell you this magic moment that occurred. So it was about 4 weeks into this, 5 weeks, I'm starting to think, I don't know, this is like a failure, nobody's gotten it, nobody's gotten it. And then the student came up to me and said, you know, Dr. Nerz, I ran out of this key intermediate in my synthesis, and what we've got to do, our team has to go back, we have to go make some more, and then we're going to purify it using column chromatography, and this is how we're going to do it. And I went, you know, bing, like the light goes off. I go, you get it, you get what you're doing procedurally. Like, in other words, what had happened was they had transformed from just like sitting there with their cookbook, cooking, and all of a sudden they're solving problems on their own. They understood like what they were trying to do, what they needed, and how they had to do it, and that they didn't have this like set procedure every week telling, you know, we're just trying to do this lab that people have done 100 times before. That's not our goal here. We're trying to make some new molecules. We really want to do this, and ultimately in my big scheme, right, my big power scheme is ultimately, maybe next year, people will take the molecules they've made and they're going to do some biological testing on them. That's how I want the course to end. And I've been working on this now for 2 years or 3 years. That's how we want it to end, and it's getting better every year. Okay, so what's the aldol mechanism? Let's look at this, and then we'll look at the other piece too. We're going to be working on the other piece in a couple weeks. The aldol mechanism is that you're taking acetone, and I want you to think about this because there's other stuff that could happen. And you're going to put some hydroxide in. And let me tell you, you have to make up your own hydroxide. You have to take 0.6 grams of sodium hydroxide and put it in 1 ml of water, and you have to scale it to your scale. Okay, 0.6 grams. Okay, so the hydroxide is going to pull a proton off this. Now, you guys, in my lecture class, we've been talking about where do you pull protons. I said generally go after protons on oxygen or in nitrogen as your first guess. But if you're in doubt, look for allylic hydrogens. And lo and behold, acetone has an allylic hydrogen. It has 6 of them. This, to a small extent at least, will pull, it's an equilibrium, will pull that hydrogen off, and we will get that anion. This will be in resonance, or we'll have another resonance form that looks like this. Okay, that's called an enolate, right? An enolate, for those who have already had it in class. Enolates are really good nucleophiles, okay? Almost like Grignard reagents or hydride. So what happens is your enolate, and I could draw it, it has another resonance form, okay? I'm going to draw it this way because the bond actually forms with the carbon, attacks the aldehyde that you have in your mixture, whatever that might be. So this acts like a nucleophile, hits the delta plus carbon, and opens up the pi system. The result of that is you have done something magnificent. You have made a carbon-carbon bond. Okay, that's really important. That's organic chemists live to make carbon-carbon bonds. Okay, it's what it's all about. Okay, so we do this. Okay, we hook this up, R groups, etc. This is going to pick up a proton. So let's say we were in ethanol. You guys are going to be in like a little, you'll have a little water around in your reaction. And you'll get you'll get the beta hydroxy carbonyl compound or ketone. Okay, so you'll have. I'm almost done. I don't have too much more to do. So you'll have this. Now notice this framework, right? So you've built this, you've built this structure, and it's not exactly like warfarin's, the piece that you put into warfarin. All right, now the thing about this is this will spontaneously, under the reaction conditions, will spontaneously undergo an alpha-beta elimination, okay? So notice it was a catalysis. When I ripped this H off, I reproduced, either hydroxide or OR minus, all right? It's a catalysis. So what happens is your base, you could use this or OH minus, is going to pull this H off. These electrons are going to come in, and that's going to pop off. Now, sometimes people are horrified by that. Like they go, how can you do that, Dr. Nerz? How can you pull a hydroxide off? You're using hydroxide as a leaving group. Hydroxide is a strong base. That is a terrible leaving group. And you're right, it's a terrible leaving group. Okay, but you have to look at the whole system here. Okay? One comment I would make is, right, all I'm doing is trading a hydroxide for a hydroxide. This is catalysis, right? I'm just like popping my catalyst back out. Trading one OH minus for another OH minus doesn't change things energetically. However, though I'm just trading a base for a base, the molecule itself is becoming much more stable because it's becoming very highly conjugated, okay? So I want you to think about that a little bit. This is the thermodynamic sinkhole for the reaction. Generally, aldols are problematic. They're problematic because this thing only partially ionizes, and because it only partially ionizes, it can actually attack itself, okay? So aldols are kind of filled with side reactions, but this aldol works extremely well because you're forming a highly conjugated product. So pretty much everyone should get some product out of their reaction. Okay? Now, realize this is not, as far as the big picture goes, you can get very, kind of lost in your reaction. But again, the class is going to make a bunch of those. Okay? You can make 2 if you want. Okay? You have some freedom here. Have fun. Have some fun in lab. Realize we are also going to make variations on this. This is something new this year that we worked on. And I have a very special research student who did a lot of work on this. So we're going to make these molecules, okay? And we're going to change the group here and the group here. And we're also possibly going to substitute nitrogen in that position. So what would I make it from? Generally speaking, thinking retrosynthetically, I would make this from groups that have R groups here and here. And we can buy a whole variety of these, or potentially have, I'm sorry, it's dark, I'll get away. Potentially have an NH2 group there. If you react that with this reagent, this is like this old-fashioned, very reactive species. If you react this with this under the right conditions, you can make that. So we're going to vary those R groups. So realize, you could almost set up sort of like a table. Like supposing you made a table and say on the top of the table, you wrote 4 different versions of this molecule. 1, 2, 3, 4, right? Maybe this is a T-butyl group. We have made, I know we have definitely made this, okay? So say you make 2 T-butyl groups, ethyl, methyl, whatever we've got, okay, whatever starting materials we have. You could make a table where you had 4, 6, 8 different versions of this where you've changed the structure a little bit, okay? Then, right, going down your table, you could have all these different alpha-beta unsaturated ketones that you've made, right? So you make all of those. Then what do you start doing? You start taking them and crossing them using those the original conditions that I gave you. And one of the things we do know is the reaction with D-pen is really quite versatile. It seems to work very, 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 very well. So you're going to play around, and some of you will do reactions we haven't done before, and they may work or they may not work. Okay, so we'll create and purify this library of compounds. That's a library of compounds, and it may have very uniform reactivity or biological activity, or very different biological activity, depending on what you change in the structure. And that's what we're kind of interested in, ultimately, is testing that biological activity. This year, that may not happen. All right, you guys are kind of the first group to do the full synthesis. Okay, so you have a big job ahead of you. Okay, but realize you have choices in this, and you're not going to be told, you know, in this very like dictatorial way, this is what we're doing this week, and you're all doing it together, and you're all doing it the same way. That's not science, okay? What we want you to do is be curious. You might be curious. You might say, I really want to see what happens when I take this compound and this compound, and I want to see if they react. Okay? So we want you to have some curiosity. Also, remember, these compounds are all potential blood thinners. So if you have any sort of medical issue with them, you should let us know. And also, generally, just be really, really, really careful, right? You do not want to be, you know, absorbing this material. So you should always be working with gloves, maybe double gloving, and working with very, very, very small quantities. Keep that in mind. Be careful in the laboratory. Wear your lab apron. Okay, so I'll see you in lab.